In today's lesson, we're going to be looking at another specific form of a hypothesis test. So a couple of lessons back, we saw what hypothesis testing was in general, and in these lectures, we're looking at specific implementations of them. And so in particular, today we're going to be looking at what's known as the t-test, and the t-test is going to come about when we have to use the t-distribution. So we saw the t-distribution with respect to confidence intervals, and today we're going to look at why it comes up in reference to hypothesis testing. So specifically with today's lesson, we're going to be looking at how we test population means in non-normally distributed populations, or when we have a normal distribution with an unknown variance. And so those were the situations where we thought about the t-distribution coming up in terms of confidence intervals. And as a result, we're going to have the same distribution coming out when we're looking at hypothesis testing. So the situation to think about is having a sample from a normal population when we don't know the variance and we don't know the mean. We'll want to test a hypothesis about the population mean. And so we could think about the null as being mu equals mu naught for some value, and then the alternative would be mu's not equal to mu naught. We can also consider either of the one-sided alternatives. So we could have the null being that mu is less than or equal to mu naught, or the null being that mu is greater than or equal to mu naught. And in either of those cases, we just define the alternative in relation to that. And then we've been looking at this test statistic, right, where you take the sample mean, you subtract off the mean under the null distribution, and then we divide by the sampling or the sample standard deviation scaled by square root of n. And when we were looking at confidence intervals, if we assume that mu naught is the correct mean, well, then we saw that this took a t-distribution with n-1 degrees of freedom. And so the same thing is going to happen here, right? And then what we can do is just take the t-distribution in place of the normal distribution that we saw last time and do p-values and such in the exact same way. Now, I'll point out something else. In the learning objectives, we talked about this being for non-normal populations, and here we're assuming a normal population still. So the other situation that this is going to work in is when we have a non-normally distributed population, but where we're taking a large sample size, right? And so what's really important here is that x bar itself is going to be normally distributed. And we've seen that if the sample size is large enough, because of the central limit theorem, then the sample mean is going to be approximately normally distributed, right? And so in that case, with a large enough sample, we can take this to still hold for non-normal populations. Now, of course, we've also seen that if your sample size is big enough, the t-distribution of n-1 is going to be approximately normally distributed. And so in this case, whether you use a t-distribution or a normal distribution isn't going to be a huge deal. But technically, the t-distribution is a little bit more correct, which is also what we talked about when we were looking at this with confidence intervals. So once you have that, we can figure out our p-values in exactly the same way. Right, so we have our t-distribution drawn on the graph here. We can think about mu naught, or you could think about it being already centered at 0, so there'd be a 0 on that line there. And then we compute our statistics value, and we think about the magnitude of it, right? And it's going to be marked in the upper tail with some probability greater than it, in the lower tail, some probability less than the negative it. And so the shaded area is the values that we could have observed for the test statistic that would be more extreme than what we actually did observe. And so the corresponding p-value is going to be the probability under those two areas, right? And so if we, this should of course say, if we observe t here, so if we observe t, then the probability that we're looking for is the probability that the absolute value of t is greater than or equal to the absolute value of what we observe, right? Now, because the t-distribution is symmetric again, this is going to be the probability that t is larger than or equal to the absolute value of t plus the probability that t is less than or equal to the negative absolute value of t. So that's just those two tail probabilities again, right? If we're using a one-sided null hypothesis, then we would only consider one tail or the other. And so in this case, we would either be looking at probability that t is greater than or equal to t, assuming that the alternative in this case would be that mu is actually greater than mu naught, or we could take probability t less than or equal to t in the other case, right? And so that's just looking at one of the two tails there. Again, we're noting that we're not going to be taking the absolute value of anything in the one-sided case, right? Because if our alternative is mu greater than or equal to mu naught, if you observe a negative value, that's actually evidence in favor of the null hypothesis. So this is just summarizing that. If the null hypothesis is greater than or equal to, then we take the lower tail. If the null hypothesis is less than or equal to, we take the upper tail. And I expressed this here with respect to the alternative, but it's the same thing. And again, we're not taking absolute values here. We can also consider the critical values instead, right? And so we could look at the 1 minus alpha over 2 and the alpha over 2 critical values and see, was our statistic outside of that interval? They'll come to the exact same conclusions, just sort of a different way of framing the problem. So if the sampling distribution is normally distributed without a known variance, then we can use the t n minus 1 to run the hypothesis tests. If it's a non-normally distributed population, but the sample size is large enough, we can also apply this test. The rejection region is still going to depend on what alternative we are considering. So in the next lesson, we're going to continue looking at these specific hypothesis tests where we consider the hypothesis tests for a sample proportion. And so I hope to see you all in that lesson.